Yeah, so I'm Hai from Hanoi. I chair the section today, and it's my pleasure to introduce the first speaker. Is Kien from the Catholic University in Leuven, Belgium, and he will talk about exponential sum, modulo p to the power m for Billion polynomials. Okay, so please.
So first of all, I want to thank the organization for inviting me to give talk here. So today I will talk about exponential sum modulo p power to the m for Billion polynomial. Do you see my screen?
Yes.
Yeah,
Okay.
it's good. Yeah, it's good.
So I will okay. So that f is a polynomial in n variable with integer coefficient, and suppose that f be a non-constant and f be greedy. So because f is a degree, so we can write f equal to f0 plus f1 plus so on to fd. For here, fi is fi is homogeneous of degree I for each I, and we denote by sf the dimension of the critical locus of fd over c. It means that it is a zero locus of the ideal generated by the derivative of first order of fd, and sorry, when nf equals 0, so I will recall a framework theorem of Berlin for exponential sum over finite field. It's a theorem 1. It means that if we have sf equals 0, then for all finite field k of large enough characteristics and all non-trivial additive characteristics psi of k, we have a bound for exponential sum over when it's running the set of k point of an, and we take the average in take the factor k power minus n to take the average of exponential sum, and this is have an upper bound by d minus 1 power to the n k power minus n over 2. Before after the result, let's consider in more general setting, and in this he replaced an by any phi by th of good property, good enough property, and f is a regular function on x, and f related to the singularity of f at infinity. In fact, when all good conditions are satisfied, can prove a bound for exponential sum with exponent minus dimension x minus nf over 2 instead of minus n over 2, and the constant d minus 1 to the n is replaced by function in terms of the complexity of f and x. For example, here I explain a bit about the complexity of a scheme H, subscheme H of an z. This depend on the number of polynomials together with the degree to define EQ. We remark that cut bound is so to not optimal in general because we have many singularity. For example, when x equal to 8 to the n, we can use a more simple argument than class method. It means that we use cutting by hyperplane section, and because this method we obtain a very simple bounds. It means that here if f arbitrary, and we have a bound of exponential sum by d minus 1 power n minus nf times k power minus n minus n over 2. And this here means that we replace n by n minus f. Okay. So the question 1 is it talks that we ask whether we can have an analog of the Linkage theorem in the setting of exponential sum over finite ring z over nz for any positive integer x. To be more precise, let's add sf is as definable. How can we bound the sum with x here run in the ring z over nz power n in terms of n as f and d. Sorry, I forgot d here. And here psi from z over nz to c star is any injective homomorphism of group. Okay, so this is the talk. My goal is I will introduce a conjecture for question 1 and give the first attempt to approach the conjecture. So first of all, I want to simplify a bit on the notion EF psi. For psi is injective homomorphism from z over nz to c star. To do this, we use the Chinese-Riemann theorem by writing n equals the product of in power of a prime pi power mi for I from 1 to r. Here pi for I1 less than I less than r are distinct primer, and mi is a 1 for all i's. And because the Chinese-Riemann theorem, we can find injective homomorphism psi I from z over pi power mi to c star for x 1 less than I less than r, such that we have the product, the order product EF psi equals the product of EF psi I for I from 1 to r. So the question 1 really give a uniform bound in terms of p and psi for equal sum EF psi, where psi from z over p and z to c star is any injective homomorphism. So to formulate a conjecture for question 1, we will recall some works of Iguza. Let P be a primer and M is at least 1. For each injective homomorphism, psi from z over p mz to c star, we observe that there sits an additive character psi tilde of qp, such that we have psi x equal to psi tilde x star x tilde for all x in z over p and z, and all lifting element x tilde in Gp of x. Note that in this case, we will say that psi tilde has conductor m psi tilde. We denote by we identify this with m. So we can write again that EF psi here equal an integral over Gp power to the n of the function c psi tilde fx dx. And this here is a Haar measure on Qp to the n, such that the volume of Gp to the n is 1. Because of this observation, we can associate f any swap function phi on Qp n and any additive character psi of Qp to an exponential sum e denoted by e phi f psi equals the integral over Qp to the n of psi f dx. And here I recall that a swap function in QP per to the n is a locally constant function with compact support. And we know that with this notation we have that one GP f psi theta equal EF psi theta, and one GP is a characteristic function of the set GP. Sorry, here is GP equal to Zn. Sorry. To give an analog of the general result class, we work on exponential sum associated with swap of what function of space form. More precise, let X be a subscheme of ENZ. Then for X prime of P, we look on the swap what function phi Px equal the characteristic function of this set. This set is set X in GP per to the n such that the reduction modulo P of X belong to the set of FP point of X. To simplify on the notation, I will write X F psi instead of E phi P X F psi. If psi is an additive character of QP. So we will go to the problem 3. It's related to the question the question 1. Means that we give a uniform bound for EHF psi in terms of P psi when psi is any additive character of conductor additive 1 of QP. And note that if X equal to be ANZ, then this becomes question 1. But here we work with more general setting with arbitrary X. So now I start to recall a result come from Iguza work and the work of Dunev and Bay. It means that I did it by theorem 4. For each prime of P, there is a positive number sigma P less than or equal plus infinity. So that for all sigma less than sigma P, there is a constant C sigma satisfy EHF psi. Sorry, I have some typo here. EHF psi less than C sigma than P power minus M psi sigma for all additive character psi of conductor additive 1. But of course, we have so many sigma P, and I will denote by sigma XF P, the maximum number satisfied theorem 4. And in particular, we can compute exactly what is sigma XFP, and we can use this. We use the Iguza-Lucas zeta function associated with Fx and F to do this. More precisely, if chi from Zp star to C star is a continuous homomorphism with a finite image, then we associate X chi F to the Iguza-Lucas zeta function. That's X chi F S defined by an integral over QP power to the n 5px ACFX every power to f dx. And here ACZ equal P power minus order PZ Z. Fx, the absolute value here is a norm in QP, and so it's a norm in QP. And we consider this function in the domain f with the real part is still bigger than 0. In fact, so we can show that this function is a rational function in P power minus f. So it can have a meromorphic continuity to C. And use this Iguza zeta function, we can show that sigma xfp equal to be the minimum takes over A in ZP of the element minus real part of F, which F is a power of this function 1 minus p power s plus 1 times the zeta function with chi equal 1, or f is the power of zeta function with chi different from 1. So to know about the constant sigma xfp, we have a question that what is the power of the equal zeta function zx chi f minus as for ab in ZP. We note that we remark that if a is not a critical value of f, then the function 1 minus t over f plus 1 times the zeta function associated with chi equal 1 and f minus a, and the zeta function associated with chi and arbitrary chi and f minus a, we chi different from 1. The function will be holomorphic. So the problem only relate to a such that a is a critical value of f. So I would recall a bit about the Bose-Sato polynomial of f. It means it's denoted by BFS. Is a monic polynomial of small degree such that there is a p in the ring of the derivative cx d over dx. Satisfy p over p assigned with assigned to f power s plus 1 equal p of x f power s. And we also some people also consider the reduced Bose-Sato polynomial of f defined by BFS over s plus 1. Note that s plus 1 always is a factor of BFS, so we can use this quotient. And so Ikuda formulate the strong mononomial conjecture. It means that let f be a non-constant polynomial in Z each 1 to each n. If you suppose that S0 is a power of this function, Z function, Z zeta function, then minus the real part of S0 is a root of the reduced Bose-Sato polynomial of f when p is large enough. And I recall that the conjecture is still open for almost k up to the end, to present. We recall that the minimum equivalent alpha theta f of f is the minimum number alpha such that b theta f minus alpha is a root of b theta f. And we remark that strong mononomial conjecture implies that sigma xfp is at least the minimum take over a in C of the minimum equivalent of f minus a if p is large enough. But indeed, in fact, there is no any result and any reason for the large enough connection of p. It means that we can expect that the strong mononomial conjecture is still hold with small p. Recently, Busata and Pupa study about the minimum equivalent alpha theta f in a series of paper on host ideal, and use Busata Pupa result. We can show that the alpha theta f minus a is at least m minus f over d for all a and c. So because this, so we expect that sigma xfp is at least n minus n over d for all p. So now we have a lower bound for sigma xfp. So we might expect some conjecture about exponential sum. In a recent work with Kruger, we state a conjecture on bound of exponential sum EF psi by conjecture 2. It means that we expect that if sigma is less than n minus n over d, then there is a constant c sigma such that we have an lower bound, an upper bound of EF psi by c sigma p power minus m sigma for all prime p, all m at least one, and all injective homomorphism psi from z over p power z to c star. And here we remark that if in an example, if f equal 1 power d plus 2xn power d, then we have a trivial calculation that EF psi equal p power m minus mn over d times p power r minus d over d. If 2 less than r less than d and m psi equivalent with r modulo d. It's this example shows that the exponent n minus nf over d should be the optimal exponent for an analog of Lorentz theorem if this analog is acid. Okay. So I want to give some remark about conjecture 2. The first variant of conjecture 2 was studied before by Iguza when he worked with indicated f is a homogeneous polynomial, and he takes sigma less than sigma 0 for a constant sigma 0 depend on a fixed resolution of singularity of f. So in this sigma 0 is not an invariant of f because it depends on the resolution of singularity. And Iguza proposed this conjecture towards a certain Poisson summation formula of the zero weight type, and with the HR condition that we have a sigma 0 is 3 bigger than 2. And this Poisson formula play an important role in Iguza's point of view for new half principle for form of degree at least 3. And here I mean half principle means that we try to find good condition on polynomial such that if f satisfies z condition and f has non-trivial solution over R and QP for all prime p, then f has a non-trivial solution over Q. The second remark that Iguza conjecture was generalized to exponential sum EHF psi associated with any non-constant polynomial f. It means that we can remove the homogeneity condition on f, and all large enough p, prime p, and all chi-third psi of collector m psi at least 2. And here I mean that if when we want to remove the homogeneity of f, we need to have a condition that m psi is at least 2. And sigma, we can consider sigma less than the lim infimum of sigma xfp when p tends to plus infinity. The third remark that we also can generalize conjecture 2 to exponential sum EHF psi. Of course, we expect that the bar holds for all p and psi of conjecture m psi is 2. I'm not sure that when we play for general x, then m psi is 1 is the conjecture can hold for m psi equal 1 or not. I don't know. So there's some case of conjecture 2 has been confirmed. The first case that the scheme associated with f minus a has non-rational similarity for some a in C, and this is follow up some recent result might work with Kruger and Musata. The second condition that the second case that we know about condition 2 is that the case of if F satisfies some non-degenerate condition with respect to its Newton free heron at the origin. And the last case that we know about condition 2 that the case n is less than 4. It is in proved by Kruger and myself. Now I want to say something about the some consequence of conjecture 2. In Ikusa view, if conjecture 2 holds, then a certain adenic Poisson summation formula will exist. And we with some extra condition that n minus n is significant than 2D. On the other hand, in the Hardy method, circle method, towards the Hart principle of F, we need to find condition for the absolute conversion of the singular series. I write this I denote by X here, and this formula is we take the sum from Q this one Q power minus n of this exponential sum associated with Fx and F and A over Q. And we remark that the current condition for the absolute conversion of F is n minus F is at least 3 times d minus 1 2 power d minus 2, given by Browning and Prenivin in 2017. And in fact, if conjecture 2 holds, then we can reduce much on the condition to n minus F is a little 2D. Then we can remove from 2 power d to 2D. Okay. So in a recent works, I can prove a weaker version of the generalization of conjecture 2 for X. More precise, I work with the exponent sigma let is less than n minus f over 2 times d minus 1. And I state here my theorem. Let X be a subscheme of A and Z, whose complexity is bounded by R and D. It means that Q can be defined by R polynomial in n variable of degree at both D. So there exists a constant C depending only on ND, such that for all private P, all analytic character psi of 2P of connector at least 2, we have a bound of equal to sum EXF psi by C times P power minus M psi times M minus NF over 2D minus 1. And here I have two remarks. If x equal to an, then theorem 6 also holds for character psi of connector 1 by using the lead Cachern and the fact that D is a lead 2. So when x equal an, we can confirm the connector 2 for sigma less than n minus nf over 2d minus 1. And the second remark that because of theorem 6, we will imply that the singular series S converges absolutely if n minus nf is at least 4 times d minus 1. And this improves the previous condition Browning and Prenivin on the conversion absolutely of X. So now I want to go to the proof of theorem 6. Most important thing in this talk. To prove the theorem 6, I need to give I need to have some step. So first step A, I denote by step A. I will solve that theorem 6 holds for large enough prime P, but with an extra factor m psi power n minus 1 is about each f psi. And I recall that here, theorem 6, we only have a c times p power minus f psi times n minus nf over 2d minus 1. But the first step I want to show that this theorem 6, how if we have an extra factor m psi power n minus 1 in the right hand side. And in the step B, we try to remove the factor m psi power n minus 1 in step A. And the last step, the step C, we show that sigma xfp is at least n minus nf over 2d minus 1 for all p, and use theorem 4. I recall theorem 4. Okay, theorem 4 means that we have a sigma less than sigma p, and sigma p is less than sigma xfp by the definition of sigma xfp. So if we can show that the sigma xfp is at least n minus nf over 2d minus 1, then we can work with small p by using theorem 4. So that's that means that why I want to show that sigma xfp is at least n minus nf over 2d minus 1. And now we continue for the step, the idea for step A. And to deal with step A, so I also need to divide this into some small steps. The first step I denote by step A1. I will try to give a uniform bound for the hypotenuse sum associated with point P in 0 to the m. And f and psi here, f P large enough, and psi is any character of QP of conductor additive. More precise, we try to show that there is a constant C depending only on N and D, such that for all large enough prime P, all additive character psi of QP of conductor additive, and all P in 0 to the M, we have this bound of exponential sum associated with P by C times M psi, C times M. Here, sorry, here I have some typo here. C times m psi n minus 1 times p power minus m psi n minus nf over 2. Over 2d minus 1. Sorry, over 2d minus 1. Okay. Step A2. So I will prove theorem 6 in case that C is irreducible and containing in the singular locus of F, with the zero locus of the ideal generated by F and the derivative of first order of F. And we prove it step 2 by trying to reduce it to step A1. Step A2 by try to reduce it to step A1. Step A3. So we try to reduce theorem 6 for last P to step A2. In fact, step A3 is easy, and is based on the fact that if we have the disjoint union of two schemes H1 and H2, then the exponential sum associated with H1 union with H2 equals the sum of exponential sum associated with H1, and the hypotenuse sum associated with H2. Moreover, if FHC contain no critical value of F, then its F psi equal 0 for all P is bigger than M. For some constant, some integer M depending only on F. And for all additive character type to P, according to lead 2. And we also remark that F has only finitely many critical values. So it means the first step we write X is union of some union of some scheme, some such scheme by intersect X with the minus the singular locus of the critical locus of F. And then now we use the fact that we can take the union, the sum of the hypotenuse sum associated with union. The union is the sum of X corresponding paths, and so we can redo the step A2 by using this trick. And note that in step A2 we work with the case that XC is irreducible and contained in the singular locus of F. And for step A2, we use the fact that we can show that the dimension of singular locus of F is less than NF. We call that NF is the singular locus of dimension of singular locus of FD. But FD is the highest homogeneous part of the homogeneous part of highest degree of F. So we can use some thing in algebraic geometry to solve this, and it is very easy. In addition, if we suppose that X is a subset of singular locus of F, and we have the dimension of X denoted by R is less than step F. Because this we can find a linear subspace S of C power to N of dimension M minus R defined over Z, such that we have the dimension of the R5 space A plus S intersect with X prime C equals 0. When A run in an open set, a suitable open subset X prime of X. In addition, we also can suppose that F of F related to S equal to F minus R. So by stringing X prime, if needed, if necessary, then for large enough prime P, one can show that we have a relation between the hypotenuse sum associated with P, F, and psi, and with the hypotenuse sum associated with P and F related to the space P plus X and psi by this formula. And this is followed by the generic principle for integral with parameter of Kluge-Lorze motivic integration theory. And here this equality holds for all P in Z for Gn, such that the reduction modulo P of capital P is belong in X prime Fp. And here also we consider M psi is a little 2. So we use the facts. And the fact that we can write Ex prime F psi equals the sum of EP F psi with P bar belong to X prime Fp. The reduction modulo P of capital P belong to the set of Fp point of X prime. And we can use it we can use the previous relation to have that this equal to be P power minus A by minus R. times the cardinality of the set of every point of x prime, and we take the maximum of all absolute value of equal sum associated with P represented to Fp plus F side, and P bar belong in x prime Fp, and we know that we suppose that F related to S equal to NF minus R, and so we call this we can estimate the equal sum associated with EP F related to P plus X side by using step A1. Of course, here we need to use a Langwell estimate because x prime, the dimension of x prime is equal to the dimension of X. So it we have some bound for x prime Fp in terms of P power to R. So this we can have some elimination for P power minus R and x prime, the number of x prime P here. And it means that we can bound for the equal sum associated with x prime, F and psi. And so now we can reduce the equal sum associated with F with X to the equal sum associated with X minus X prime. Is we can suppose that this is dimension is 6 less than R, less than the dimension of X. So we can use induction on the dimension of X. And of course, we need to use step A1 to finish step A2. And here I can I have a remark that for all this process, we still need to make sure that we can use the bound of step one A1 for EP F related to F to P plus X side, and we need to control the complexity of X minus X prime. But we can do this by use some generic principle in arithmetic geometry. But it's not it's quite detailed, and so I don't want to say more here. The most interesting part is the proof of set A1. The most interesting part is in the proof of step A1. To prove step A1, we need to use a transfer principle for bound of equal sum. And this will have to relay equal sum modulo P power to the F to equal sum over finite field. This comes from my recent work with Vey. I will recall this in more detail. This is the most interesting here. I will write for a tuple xt in gt power to the n by x1t to xnt, and with here xit equals the sum of xij t power j, the x added 0. Then we can write fxt equals the sum of fj xj tj, where fj is a polynomial in variable xj with the tuple ik with the condition. As also write xj equal to sorry, is some table here. Xj here equal to x0 and x tilde j, not x tilde m-1. We call fj the zeta set polynomial f. If h is subscript of a and z, we can view fj. The fj is as a regular function on the scheme x times a z power n j. So the lemma 7, this comes from my work with Vey. It means that if we can have a bound for here equal sum associated with the sum over finite field associated with the scheme xi times an power m-1n of this psi a f0 x0 plus b f m-1 x m-1 is less than cm power cm times p power minus m sigma I, for own I in Z. Here, each I from I with I in Z be a family of subscheme of A and Z, such that sigma I in Z be a family of a positive real number, and we have our own Z condition like this. I claim that there exists an integer m and a positive constant c. The c depend on n d and the cm with m less than l and d for some function l in terms of n and d. So that for all I in J, for all p at least m and all additive character psi of qp of pointer m psi is at least 1, we have an upper bound of equals sum by this in terms of with a factor m psi power m minus 1. If we know that if it equal p and x0 equal p mod p, then we can rewrite the absolute value of this equal sum associated with af0 plus bf m minus 1 by the equal sum associated with the polynomial bf m minus 1. And here we use the mark that the polynomial f m minus 1 is a weighted homogeneous polynomial in x tilde m minus 1. And so we can use a consequent of class bound for weighted homogeneous polynomial given by Kruger to see that we have an upper bound for equal sum of this function f m minus 1 in the affine space and power m minus 1 n. We know that here we need to put, we only know about the case when x equal p because we have we can take the equal sum over x tilde in the affine line, the affine space. In affine space. So we can have bound in terms of x tilde zm-1 with zm-1 denoted by the function as a polynomial in x tilde given by take the x0 is constant, and x tilde here is a dimension of the singular code of zm-1. And so I'll be called by let Zf is a Jacobian ideal of f, and by use a simple computation of and the work of Musala on local logical threshold, we can show that if p is large enough and capital P mod p is a critical point of f, then f tilde zm-1 less than mn minus m minus 1 local logical threshold cf at q for some critical point q of f with q bar equal p bar. And here I mean that local the local logical threshold of an ideal a at x defined by supremum of f at 0 when the function is integral around x. And here fi1 to fr is a set of generating element of A. We know that by property of local threshold, we know that the local threshold A at x is less than n for all A and x. So we can use it to show the bound for exponential sum by cm times p power minus m local threshold jf at q over 2. And now, so we can apply lemma 7 to family p with p in a point in Zn. And with the mark that we can show that the local threshold jf at q is at least m minus n over d minus 1 for all critical point q of f. So now we can finish step A. For step B, we recall a consequence of recent result of Kruger, Kola, and Musata that they see the constant C depending only on n d. such that for all last enough P and all character side to P of character M side addict 2, and HC is subset of M minus 1 0, and then we have a bound of exponential sum by MC M side power n minus 1 with exponent here, with exponent here is m minus 1 local 3 solve of the ideal f plus j f square at x. And here I mean that the local 3 solve of this ideal at x equals the minimum of all local 3 solve of this ideal at every point x in HC intersect with the zero local code of this ideal. And we also remark that one can show that the non-canonical solve f plus cf zf square at x minus n minus nf over 2d minus 1 is at least is bigger than r and d, and bigger than 0 if d is bigger than 2 for a suitable function r in terms of n and d. And so because of it, and the Coca-Cola-Mustata result, we can show that the theorem 6 for M is at least N L M at least L and D, and for all large enough P. Now for large enough M and large enough P, we can confirm theorem 6 by Coca-Cola and Mustata result. But for small n, for large p and small m, we use step A to prove for theorem 6. So it means that we finished steps B. Lastly, for step C, we can use an idea of the idea from the paper of Coca-Cola and Mustata to show that for x prime p and x epsilon addict 0, we have that the exponential sum e x epsilon will be equal to be the exponential sum in over the set x in gp power to the n upon x in gp power to the n, such that 2 order p jf x e as it m minus 1. And we can use a very simple calculation to show that this power is less than cph epsilon times p power minus m, else it locally equal to resolve jf square at x minus epsilon, and with some constant c ph epsilon depend only on ph epsilon. And the last inequality followed by property of the equals local zeta function associated with ZF. So theorem 4 and the definition of sigma xfp implies that sigma xfp is at least n minus nf over 2d minus 1, and so we can finish step C, and we finish the proof of theorem 6. So I finished my talk here. So thank you for your attention.
Yeah, thank you very much. Are there any questions or comments? So the result that you obtained, does it have any application to the hash principle that you mentioned for, say, dimension 3?
Sorry,
okay, Hasse principle.
Yes.
This is kind of motivation for you, yeah. And, so
yes, this kind of motivation, yes. But to work with hash principle, we read enough because we need to estimate for the minor arcs in the Hardy method, Soko method. Yeah, but we try to find some application of this to hash principle in the future. Yeah.
Okay, so if there are no more questions, let's thanks Nguyễn Hữu Kien. And we will have 20 minutes until the second lecture today. Yeah.